Hello everyone, I hope you are doing well, and this is chapter 1, bonding and geometry. In this chapter I have included hybridization, sigma and pi, resonance, stability of carbocation, carbanion as well, and a concept of aromatic, anti-aromatic and non-aromatic compounds. Generally aromatic and anti-aromatic is a part of aromatic reactions, but I have included here because it is directly related to resonance. If you have an idea about the resonance, then you can answer those questions. So let's start the very first one. So this is the front page, this is chapter 1, bonding and molecular geometry. And now move to very first question. It is talking about which of the following carbon is likely possess tetrahedral geometry. So tetrahedral means sp3 and sp3 means 4 sigma bond. Okay, so we can solve in this way. Look at this carbon number 1. If you expand this structure, it should be like this. This is carbon 1. This is carbon 1. Have 2 hydrogen and then double bond, and again we have a carbon with the hydrogen, and then there is again 2 hydrogen on a carbon, and then C double bond O, and then here OH like this. Oxygen has 2 lone pair, we all know. Okay, so this is the expandable form of this compound, and it is talking about which one is tetrahedral. It means we have to find out all the carbons hybridization state, so it can give you a very clear idea. So if you look at this carbon, it has 3 sigma bond because double bond has just 1. So 1, 1 and 1, which means sp2. If you look at this carbon, carbon number 2, this is carbon 1, this is carbon 2. Carbon 2 also have the 3 sigma bond around that particular carbon, so this is also sp2. And this carbon has how many sigma bond? 2 hydrogen. Here we have 1 in the up, 1 in the down, 1 in the left, 1 in the right, so 4 means sp3. And this carbon is 3 sigma bond, sp2. Clear? So the numbering is done in the 1, 2, 3, 4, only the carbon atoms. This is my 3, this is 4. So sp3 is my number 3, and that is tetrahedral. Clear? So answer will be 3. Now the next question, the number of pi bond in CH2 double bond, CH single bond, CH double bond, like this. So listen, whenever the question is related to sigma bond, then you have to draw the expandable form if it is given in the bond line. But this is quite clear here. We have a double and triple bond, so you can directly count. Double bond have 1 pi and triple bond we have 2 pi. So here we have a double bond, which means 1 pi. Here we have another double bond, again 1 pi. And here we have triple bond, which means 2 pi. So how many pi we have? 2, 3 and 4. So answer will be B. Now the next question. It is talking about the stability of carbocation. And we all knew carbocation is generally tertiary is more stable than secondary and then primary. So this is secondary carbocation because it is bonded with 2 carbon chains, one in the right, one in the left. This is again secondary. This one is a tertiary because 3 carbon here, 1, 2, and this is 3. And this is just bonded with a carbon, this is primary. So tertiary is this one, number C, so C is more stable. Now the next. Which of the following carbocation is most stable? You can zoom this, yeah. Which of the following carbocation is most stable? So what does it mean, this pH? pH means phenyl. Phenyl is like benzene. So here we have 3 phenyl ring like this. If you are going to draw the A1, it is like this, C plus, and with 3 benzene like this. And here we have another one. Can you see? So we all knew benzene, if carbocation is directly bonded to benzene, then it has a resonance in the ring. So here we have 3 benzene ring, means more resonance structure here, and here just 1 benzene ring, like this. Here also resonance but less resonance, and here you have two benzene ring like this. Clear? And this one has no benzene, only methyl. So simple thing is that this is my most stable. Why? Because more benzene ring. Then this is the less stable. Then this one is a C1, and then last one is my D. If you are going to arrange them in the decreasing order, then the answer will be A, after that B, then we have C, and then we have D. This is the decreasing order of stability, and the right choice here will be A. Which of the following species is isoelectronic with ammonia? So let's count the electron of ammonia. We all knew nitrogen has a lone pair. So look at here, whenever if you draw the structure of this ammonia molecule, so a single bond means 2 electron, okay? So 2 to 4 to 6, and a lone pair also has 2. So overall 8 electron here, 8 electron. Now count here, CH3 with a radical. Radical means just 1 electron. So here 3, 2 to 4 to 6 and 1, 7 electron. This is 7 electron. Look at this negative charge with the CH3. We can count negative as 2. So 6 plus 2, 8 electron here. Here just 6 electron. Why? Because positive charge has 0 electron. And this is a lone pair, and 2 hydrogen here we have. So 2 hydrogen means 4 electron, and a lone pair, so 6 electron. Clear? This is nitrogen having 8 electron. So CH3 minus is also have 8 electron. So both have a same number of electron. That is called isoelectronic. Iso means same, electronic means electrons. Now the next is least stable carbon ion. This is very good question. Least stable carbon ion. We all knew carbocation is stabilized by electron donating group. Clear? And carbon ion is stabilized by electron withdrawing group. Clear? So if your carbon ion has donating one, then unstable means cross connectivity. What does it mean, cross? Like if you are connecting negative with the donating group, then it is unstable, and positive with the electron withdrawing, unstable. Make sense? So here we have the carbon ion. So this carbon ion, the very first one, if you are going to draw, this is negative and have 3 methyl like this. 1, 2 and 3. As you can see here, we have donor 1. Methyl is a donor 1. So here we have 3 donors. Clear? And here you have CN1, C negative, CN, CN, and again we have CN. Clear? So CN is a withdrawing one, so it will stabilize the carbon ion because CN is a withdrawing one. NO2 is also a withdrawing one, and C6H5 means benzene, and it means there is a resonance. Clear? Because benzene has an alternate pi bond, so you know that this negative is in resonance with the double bond. So the best in the given option is A. Why? Because here we have all the donor one, and donor is attached to a carbon ion, that means unstable. If you have a carbocation, then you can see the donating group, but not the withdrawing. So this is carbon ion, and it is talking about least stable. Least stable is option A. Why? Because there is a donor. Find out the most stable free radical. You know, free radical also have same trend like carbocation, means resonance stabilized radical will be most stable, and after that the tertiary, secondary and primary. I can write here the resonance stabilized carbocation and radical is more stable, then tertiary, then secondary and then primary. So here we have you can see this resonance, the double bond with the radical is in resonance. This is resonance. Here no resonance, here no resonance, and here no resonance. So resonance dominates over tertiary, secondary and primary. So answer will be A. So in this page we have 1 to 7 questions, and this is all about the carbocation and carbon ion. Now the next is, I have done this 2 question in my acid base problem sheet, and I am going to discuss here as well. Okay. So it is talking about the strongest acid, and for the strongest acid, eliminate the H and look at the negative charge over the oxygen here. And here you can remove from, this is something wrong here, this is CH2, so you can keep this CH3, and once you remove a hydrogen there is a negative, any side, either left or right, because it is symmetrical, and here we have this negative. Clear? So in cardio, if you are going to apply, what is C? C stands for charge. Charge means positive is more acidic than neutral, and then negative charge. So here everyone is my negative after deprotonation. So C fails here. Next is atom. Atom means if you are moving left to right in a periodic table, electronegativity increases and acidic strength also increases, okay? And if you're moving top to bottom, size increases and acidic strength also increases. So here you have two different kind of atom. One is a oxygen and one a carbon. Oxygen and carbon, they both have negative. Clear? So oxygen is much more better than carbon, so D fails here, because the rest of the option have negative or oxygen. So atom is going to fail. Now the next is resonance. So resonance is only in the option C and B, because both are in resonance, the negative charge. So simple thing is that this last time I discussed, this COO minus this one, this forms identical resonance structure. You know, this will donate like this and it breaks. So here O negative, double bond O. If you compare these two structures, here oxygen have a negative, here oxygen have a negative, and here C double bond O, C double bond O. So this is identical, but in this case, if you donate like this and CO break in this, carbon double bond break in this way, so you know it forms non-identical resonance structure, and once you draw the resonance structure, negative on a carbon here, and if you draw the resonance structure of this one, oxygen negative here, and here also oxygen negative. So negative on more electronegative is more stable. Simply you can say identical resonance is more stable than non-identical. That's why this conjugate base is more stable, and it should be C. Acid having highest value of Ka, most acidic. So again same thing, just eliminate the hydrogens. Here negative, here negative, here negative, here negative. We have learned this before. Carboxylic is better than alcohol in terms of acidity because of identical resonance structure. So there is a competition between A and B only. Okay, not C and D, because there is an oxygen of alcohol here. Now the next between A and B, we know that cardio. So C fails A as well as resonance. Now the next is dipole induction. We all knew acidic strength is increases by electron withdrawing group. Okay, donating can destabilize. So here we have a methyl, which is a donor one, and this one has hydrogen. Hydrogen is neither a donor nor electron withdrawing. So this is much better than this CH3. So we will go with option A. That is most stable conjugate base, and that's why the most acidic. Now the next one, sorry. Okay. Next question is talking about which of the following compound cannot show resonance. Cannot show resonance. I have discussed in my videos. I said that whenever you have a species like positive charge, negative charge, lone pair, radical, and vacant orbital and double bond, if these species are in alternate, means this is called as conjugate species. This is called as conjugate species. When these species are in alternate position, that is the condition of resonance. Means between two conjugate species there should be a single bond. This is the condition of resonance. Clear? So let's start here. You can see double bond is a conjugate species. Here double bond is also conjugate species, and both are separated by a single bond, which means option A is in resonance. Now look at option C. This lone pair is a conjugate species. Double bond is also a conjugate species, and here we have again a single bond, again a resonance because we have a single bond. Now look at this B. Lone pair is a conjugate species, double bond is a conjugate species, and they have a single bond, means resonance, as well as this side is also in resonance. Why? Because this conjugate and this conjugate is separated by a single bond. Now option number D, because oxygen has a lone pair, so we can put here oxygen. This lone pair is a conjugate species, any one of them, top one or bottom, it doesn't matter. Double bond is also a conjugate species, but here we have more than one single bond, more than one. So if you have more than one single bond, it means it is not in resonance. So the right choice will be D. Now the next, identify the conjugated compound. Again, conjugated have the same concept. It should be separated by a single bond. So look at option A, lone pair on nitrogen is a conjugate species. This is a double bond is a conjugate species. Both are separated by two single bonds, so no resonance. Here also you can see both double bond has more than one single bond. No resonance. This CH2 is a conjugate species and this double bond is also conjugate species, but again they have more than one single bond, so no resonance. And now look at this one, the C1, it is P plus CH. I think there is a mistake some in the option. I think it should be here you can keep a negative, suppose. Clear? Yeah, there is a mistake in option C, because this is not a balance form. You can see CH2CH PPS3, okay? Or even you can keep a double bond here as well. Look at here. We can keep here double bond. Why? Because this is CH2 and this is CH. So if you balance this, there is a double bond. So you can keep here double bond. And this is in resonance. Why? The positive charge you can consider as a conjugate species. Double bond is a conjugate species. And here we have a single bond. It is separated by a single bond. That means resonance. Clear? So here you can keep a double bond. Okay. Question 11, option C. Now the next is question 12. The most stable carbocation from the among of the following. Again we can say here tertiary is more stable than secondary than primary. So this is secondary, this is primary, this is primary, and this is tertiary. So right choice will be B. Consider the following carbocation and they arrange them in the decreasing order of their sequence. So we can draw like this. Look at here, A, C6H5CH2 plus, it means it is like this, CH2 plus, and we have a ring like this. So this is a resonance with one benzene. What about the third one? If you draw the third one, CH plus, have a CH3 in the right, and the left side we have a benzene. Clear? Here this is just a primary carbocation with resonance, and this is my secondary carbocation with resonance. Now draw the third one, second one, sorry. Ring, CH2, and this is CH2 plus. In this case we have no resonance, okay? Now the fourth one, a ring, CH2, and then there is a C plus, and we have 2-methyl. I told you resonance dominates, okay? Resonance dominates, then tertiary, then secondary, then primary. So this is the second, and the second structure is not in resonance. Why? Because this benzene ring means alternate double bond. I can draw here like this. Ring inside the ring means alternate double bond like this. And you can see this positive is a conjugate species. Here double bond is a conjugate, and both are separated by two single bond, not one single. So whenever you have more than one single bond between two conjugate species, that is not in resonance. So no resonance, as well as in this case no resonance. Resonance containing compounds are 1 and 3rd, but this is just a primary with resonance, and this is my secondary with resonance. So resonance is common, but this is secondary. That's why third one is the most stable. So the right choice, we have to arrange them in the decreasing order. So we can say the third one is the most stable. Which option? Third one is the most. Oh, there is something wrong in this case. Third, 1, 2, 4. This is 1 even. You can write like that. Hmm. I think third one is the most stable. Okay. Then first. Third one is most. Don't look at the option. Maybe sometimes it can be wrong in typing. So third is my most stable. Why? Because resonance and secondary. And after that we have the resonance on the first one, third first. And then we have this one. The fourth one, why? Because this is tertiary carbocation. So tertiary one, you can see this is tertiary and this is primary. So third, first, then fourth, and in the last, second. So this is the right choice. Third, first, fourth, and second. Third, first, fourth, and second. Yeah, it is not in this list, so you can mark here. So this one we have the wrong options. So we can say third, first, fourth, and second. Now the next one is 14th. We have two compound, and it is talking about, are there resonance structures? Yes. Why? Because you know it will move here and CO break like this. So there is a negative, it missed here. So keep negative. And now you can see this CH2 has a CH2 double bond and this is O minus. So resonance structures have same connectivity as well as same atoms. You can see here this is CH2, this is CH2. Here we have C and O, here we have C and O, and this is CH3, this is CH3. So resonance structure is the right choice. Why geometrical is not right? Because geometrical observed in carbon double bond carbon. If you have learned cis and trans, then cis and trans are geometrical isomer. But this is not like cis and trans because this is CO bond, not carbon-carbon double bond. So this is wrong. Tautomer. Tautomer is something like keto form to enol form. What is keto and enol? Look at this compound CH3CHO and look at this one CH2 double bond C, here OH and here H. This is enol, this is keto form. So keto and enols are the tautomers. Okay, you can see here we have different functional group. This is aldehyde, this is alcohol. So tautomers is a kind of isomer where we have two different structure, not the same. But here we have same structure, difference in their electron movements, and that is called resonance. Optical isomer is related to chiral center, and you can see there is no chiral center. Makes sense? So D is wrong as well. So in this page we have question number 13, which something wrong in the question 13, but this is the right trend. Okay, the stability. Now move to the next question, 15th. It is talking about among the following the aromatic compound. So first of all, you should know what is the condition of any compound can be aromatic. And here we can say any compound can be aromatic. There is a few conditions. Condition number 1, must be cyclic, must be cyclic. I have discussed this topic in my video. Second condition, must be cyclic conjugated, must be cyclic conjugated. C dot C means cyclic conjugated. And the third point is planar, must be planar. Planar means sp2. And whenever any system is cyclic conjugated, 99% it will be planar. And the fourth one is what? Whenever you have 2, 6, 10 and 14 pi electron, conjugated pi electron, then entire thing will be aromatic. So look at here, this is cyclic conjugated, everyone is in the alternate. This is planar as well. And how many conjugated pi electron? I discussed in my videos, you can watch. The positive charge has 0 pi electron and double bond has 2. So overall we have 2 pi electron, and 2 pi electron means aromatic. So compound A is aromatic. Now look at C. C is cyclic conjugated, And planar, how many pi electron? 2 and 2, 4 pi electron. So 4 pi electron means anti-aromatic. So this is my anti-aromatic. This one, cyclic conjugated planar, and how many conjugated pi electron? 2 and 2, 4. 4 means again anti-aromatic because positive charge has 0 pi electron. And this is the D, cyclic conjugated planar, and how many conjugated? 2 and 2, 4. 4 means anti-aromatic. Now question 16, it is talking about the most stable free radical. I said that same concept as carbocation. Look at the resonance. You know, this CH2 is primary but without resonance. Why? If you go and draw this is CH2, then again CH2, and then ring. So you can see this is not in resonance. This CH3 is bonded with the CH2, which is the donor one. Yes, this one is the left side, we have a benzene ring, right hand side we have a methyl. So this is secondary with resonance, and that is the most stable. C6H5 means benzene ring. Which of the following ion is most stable? Most stable. So this is primary, this is secondary, this is primary, and this is tertiary. So we all knew tertiary carbocation is much more stable than the rest. So 17C. Now the next. Question number 18, it is talking about which of the following is the least stable? Least stable. Easy, very easy. This is a primary just, that's why the least is stable. Clear? This is tertiary, stable. This is secondary and one side with resonance. C6H5 means benzene, and this is just a secondary without resonance. Suppose we have to set here the decreasing order of the stability. So we can say D is the most stable. Why? Because D has a secondary with the resonance, and resonance dominates here. Okay. And then we can say C. And then we have B and A. You know, in some books, resonance stabilize and this tertiary with the methyl one. They can say like C is more stable than D. This is a controversial one, okay? Because there is a effect called hyperconjugation. So hyperconjugation means all the three methyls is applying here hyperconjugation effect on the carbocation, and that gives you the most stability. It means it is going to dominate over the resonance as well. Okay, if you have just one benzene and this tertiary group. So if you take my opinion, it can be between D and C, and I would like to say C is more stable than D, then B, and then A. This is the correct trend. Okay, here this is an exceptional case, you can say, because here the hyperconjugation, the full impact of hyperconjugation. And I think in DAT you should know only the resonance and tertiary, secondary and primary, and that's it. And we can here say like this is secondary with the resonance, but this question is talking about least stable, so least is here primary. Now question 19. Which of the following resonance will be possible? So you can again do the same thing. Resonance is what? Alternate, means between two conjugate species there should be a single bond. So as you can see, this is conjugate species, this is conjugate species, and here we have a single bond, so B is the right choice. In the D1, conjugate species but more than one single bond, so D is wrong. CHO is like this, C double bond OH, so this is a conjugate species, but again we have more than one single bond, so A is wrong. And this is just a CH3CO CH3, there is no other conjugate species. This is the structure of CH3CO CH3. So this is not in resonance as well. The right choice is here B. Heterolytic bond fission of a covalent bond in organic molecule. What is heterolytic? Let me explain you. Suppose we have a CX bond, and I am saying electronegativity of X is greater than carbon. So it will break towards X, and as a result of it, X is going to pull the electron of this bonded pair, so X will be negative and this carbon will be positive. So this type of breaking is called as heterolytic. Why? Because there is a difference in the electronegativity. And it produces cation and anion. This carbon positive is cation and X minus is my anion. If you have same type of group like this, so both electronegative values are same. So it breaks like this, half here, so it will produce radical. Clear? So homolytic. This is called homolytic because there is no difference in electronegativity. And heterolytic produces cation and anion, and homolytic produces only radical. Now 21, which of the following radical is the most stable? Again you can do the same thing, resonance. So this is my tertiary with resonance, This is primary only, no resonance. This is just a methyl radical. This is just a CH radical. This is not in resonance because on a same carbon we have a radical and double bond. That is not alternate, okay? This is in alternate. It's radical and double bond. We have a single bond here. So resonance with tertiary is only option A, and that is the right choice. The order of stability of the following carbocation. So let's find out this one. This is primary with resonance, 1 degree plus resonance. This is just a primary without resonance, and this is primary with resonance. So now the thing is very simple we have. So this is the very interesting one, the first case and third case, because both are primary but resonance. But the problem is this is just a one double bond in alternate, means just a one resonance structure. But in this case we have multiple resonance structures because more double bond, okay? So the right choice will be the third. Third is the most stable because it will form more resonance structure than first, and in the last second. So third, first, second. Which option? Option B. Third, first, and then second. Clear? Now 23. Which of the following pair of the structure on the right major resonance contributor? Means it is talking about in which of the following option the right structure is major contributor. So look at some terminology. Major contributor means most stable. Most stable. And resonance contributor means resonance structure. Clear? So simply it is talking about in which option the right is a major contributor, means most stable to the left. So look at the compound A. In the resonance structures stability, I discussed this topic in my video. Let me explain this to you. The very first rule I told you, more the double bond, more will be stability. More double bond. More double bond, more will be stability. And after that, rule 2. You have to apply each rule one by one. If rule 1 is not working, then rule 2. Rule 2 is saying neutral compound is more stable than charge. Neutral is more stable than charge. Rule 3, I said that negative charge on more electronegative element. Negative charge on more electronegative element is more stable. And the last rule is what? Opposite charges closer are more stable. Opposite charges closer are more stable. Closer are more stable. So if you look at option A, I said that more the double bond, more stability. So they have equal number of double bond, as you can see. Now rule 2, neutral is more stable than charge. So the left structure is my neutral and this is my charged one because we have positive and negative. So the left is more stable. Clear? Second question. Again we have to apply the same thing. More double bond, they have equal number of double bond. Second, neutral is more stable than charge. So this is my neutral, this is charged. So again the left one is more stable. Next, there is something wrong in this one because you have to, once you are going to break this CO bond, it will be like this. it will be like this, O negative, this is plus, and there is a double bond. Clear? So please correct this, there is no double bond, it's just a single bond. Okay, this is just a single bond. So in this case, C and the right one, the left and right one, I said that rule number one, more the double bond, more stability. So you can say the left is more stable, but there is a something extra. The most stable structures are the aromatic structures. Okay, if you are going to compare anything with the aromatic is always be the most stable one. So in the left and right, you can see this is my ring, this is my ring, and this is cyclic, this is cyclic, this is cyclic conjugated, and this is planar as well. And how many conjugated pi electron inside the ring? Just 2 pi. So 2 pi electron means aromatic. So the right structure is aromatic, the left is not aromatic. The resonance form of this is aromatic. Makes sense? So it will move towards the charge form. It will move towards the charge form. So the right structure is more stable in the option C. And this is again the D. Again you can say more the double bond, more stability. So it has a double bond, and this is a charged one. So D again, the left one is more stable. So it is talking about the right. The right. So right one is what? The option number C. Now the next. Which of the following resonance structure of the formic acid, arrange them in the decreasing order of stability? So what is the rule 1? Rule 1 is more the double bond, more stability. They have equal number of double bond in all the example, equal number of double bond. Okay, rule 2, neutral. Which one is my neutral? This first. First one is a neutral one, okay. So first is the most stable structure. And they are all charged one, here plus minus, here plus minus, here plus minus. Now be smart. Whenever you are going to solve the questions, always look at the options. In the given option, the 1 is the most stable in only in the B. And that's why B is only the right choice. Clear? Do not move forward. If you have your answer, then don't waste your time. Clear? Now the next is 25. Which will be the least stable resonance structure? Least stable it is talking about. I discussed the stability rule, but here write down a note point. I said that opposite charges closer are more stable in the very last rule of resonance structures comparison. I said that opposite charges closer are more stable, but there is an extra thing. Same charges in the neighboring position are unstable. We can say here same charges in adjacent position is highly unstable, So same charge means if you have a lone pair, negative charge. Why? Because lone pair is electron rich and negative is also electron rich. If you have both electron rich in the adjacent carbon, then it is repulsive in nature. Same with the positive. Clear? So if you have same charges in the adjacent position, it will repel to each other, and that is an instability of the intermediates. So you can see here 25. In option A, you can see here nitrogen has a lone pair and carbon has a negative charge. Make sense? So these two are the electron rich one and they are very close, adjacent. So this is the instability case, okay. So least stable will be option A. And the next one is 26. Which of the following pair of structure is not a pair of resonance structure? You know, once you break like this, so here carbon will be positive, triple bond break down into double, and this nitrogen will be neutral. Clear? So this is the resonance form. Second, Listen, this compound is not in resonance. This is not in resonance. Why? There is no conjugation. There is no other conjugate species which are in alternate. So if this is not in resonance, then how can you generate its resonance structure? Resonance structure only be possible when the given compound are conjugated or in resonance. So B is wrong. Clear? And rest, we are not going to check the rest of the options because we have the right choice of B. B is not a pair of resonance. Now the next 27. Which of the following pair of structure does not represent the resonance structure? So I said that earlier, in resonance structure, atom cannot change its position. Only the electron's movement takes place. Here you have oxygen and here you have OH. So there is a transfer of atom here. Okay, so this is not the resonance structure. While rest are resonance structure because atoms are same, CH3, 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 OH, like this, you know. So only option A. Now the next 28. Which of the following is a pair of resonance structure? Again, same thing, pair of resonance structure. So if you are going to move double bond towards the positive, so there is a positive charge and this carbon has a bonded arrow, so there is a double bond and this is the resonance structure. If you look at the B, this is just oxygen and this is OH, so this is not the resonance structure. This is not in resonance. Why? Because this is just a one single double bond, so this is not a conjugated system. And this is also not conjugated. Why? Because positive and double bond had separated by two single bond. Okay, so this is not the resonance. Only option A is the right choice. I discussed how to draw the resonance structure in my video, so you can watch. Now the next 29, this is talking about the most stable form. You know, I discussed whenever you are going to check the stability, so preference is given to resonance, then tertiary, then secondary, and then primary. So this is a tertiary one, and this is the oxygen have a lone pair, this is oxygen have a lone pair, and this is oxygen have a lone pair. So resonance only in the option C. Clear? Resonance only in the option C. Why? Because this lone pair and positive charge, this is a conjugate species, this is a conjugate species, and separated by a single bond. So this is in resonance. Clear? And this case and this case are different in nature. So don't say both are tertiary, so why they are not the most stable? This is tertiary, absolutely right. This is also tertiary. But this tertiary and this tertiary, there is a difference. Here we have a CH2 group, so both will apply hyperconjugation effect, but this is the hyperconjugation in its like most stable, most strength. The hyperconjugation is here like highly in nature, not here. Hyperconjugation provides stability to a carbocation. And let me discuss what is hyperconjugation. Suppose here we have a tertiary carbocation and here we have a secondary carbocation. And this is also secondary. Okay. So most of the student can say this first is the most stable. Why? Because of tertiary. Because of tertiary. You can say this is the most stable because of tertiary. But they are going to fail to check the stability of second and third because both are secondary carbocation. So hyperconjugation deals with the study of same degree of carbocation's stability. Means you can compare tertiary, secondary and primary as well on the basis of hyperconjugation, but it will give you a very clear idea once you have same type of carbocation like secondary or primary. So what is hyperconjugation? Look at here. Whenever you have a positive charge, the neighboring carbon is called alpha carbon. This and this. This is my positive charge. I said that neighboring carbon is called alpha carbon. The very first neighbor. This is alpha, and this is alpha. And what is alpha hydrogen? The hydrogen of alpha carbon. So first has 9 alpha hydrogen. Second, how many alpha carbon? This and this only, because this is directly bonded with the carbocation. And how many alpha H here? 5. And what about here? This is alpha. So here alpha H is just 4. Clear? So simple thing is that more the alpha hydrogen, more will be stability, and that is called hyperconjugation. So the stability order will be first, and then the second, and then the third one. Clear? So this is a tertiary, and this is also tertiary, the D1. But how many alpha H here? Same type of alpha H, yes, 336 and 2 here, 8. And here 336 to 8. This is alpha, this is alpha, this is alpha. This is alpha, this is alpha, and this is alpha. But here you have an OH group. OH is an electron withdrawing one. So it will destabilize the carbocation. But here we don't have any OH group, okay? If OH is in the alternate with the positive charge, then resonance. If OH is not in alternate, then it will act as an electron withdrawing. Here as well it will act as electron withdrawing. Why? Because this is not in resonance. Clear? But this case OH is in resonance, so it will donate like this, and that increases the stability. So C is more stable. Arrange the following carbocation in the decreasing order of stability. Listen, I said that aromatic carbocations are always the most stable. And you can see this is my aromatic. Why? Because 6 pi electron, this is cyclic, conjugated, planar, and 6 pi means aromatic. This is just a resonance with primary. This is just a resonance with primary. But yes, benzene has more resonance structure than this. So R is definitely stable than R is more stable than Q. Why? Because in R it will form more resonance structure. And Q is more stable than S because there is no resonance structure. And the most stable will be my P. So the right choice here, PRQS. PRQS. Clear? P is aromatic. Q and R both have resonance, but R form more resonance structures and Q form less resonance structure. That's why P, R, and then Q, and the last S because no resonance. Now the last one is 31. The most stabilized cation. So look at here. This is resonance with primary. This is resonance with tertiary, You can see double bond is in the alternate. This is resonance, plus this is tertiary as well, plus both side resonance, this side as well as this side. Can you see this? Both side resonance. So both side resonance means more stable form. And this is my just secondary without resonance. Clear? And now everything is clear. The most stable form will be what? The tertiary with more resonance, and that is option C. Both side resonance and tertiary. Clear? So this is all about the chapter 1, bonding and molecular geometry. I have done 2 chapters, chapter 1 and chapter 2, acid and base, and the next will be stereochemistry. Okay, so there will be another 30 questions in which I will cover all the topics. So thank you so much for watching this.